This lesson is over 8.3 geometric sequences. What do these two sequences have in common? Go ahead and pause and see if you can notice something. When looking at this first sequence, we notice that 12 times 3 is 36, 36 times 3 is 108, etc. And on the bottom, we have 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. What's happening is we have a common ratio. Sequences that have a common ratio are known as geometric sequences. And the wonderful thing about having a geometric sequence is that it comes with its very own nth term definition formula. A sub n equals a sub 1 times r to the n minus 1. We're already familiar with a sub n and a sub 1 and using n in our definition, but r is our new thing today, and that r stands for the common ratio. So wonder if we wanted to define this sequence using our new definition. All we would have to do is say a sub n equals the first term, which is 2, times r, which is 2, raised to the n minus 1. We wanted to define this sequence we would simply have a sub n equals 12, the first term, times 3, the common ratio, raised to the n minus 1. Why don't you guys try this one? Go ahead and put it on pause, write this down in your notebook, and see if you can figure out the nth term definition. Okay, hopefully you have down a sub n equals negative 1/3, which is the first term, times negative 1/3 to the n minus 1, because negative 1/3 is our multiplier. I hope you noticed that we've got an oscillating sequence here, negative, positive, and so now we don't need to think about using negative 1 raised to the nth power or negative 1 raised to the nth plus 1 power, because our geometric sequence formula takes care of that for us. But looking at this answer, it kind of bothers me, all those negative 1/3, and I'm wondering, can we simplify this? How about this? What do you think of that? Can we take this formula and change to that? Why is it true? I'm going to challenge you to remember your exponent rules. Look at this. That's the same thing as this. Think about that. If you don't understand why these two are equal, please ask me in class. Okay, so that's our basic type of geometric sequence problems. Another type of geometric sequence problem is something like this. If a sub 4 equals 125 and a sub 10 equals 125 over 64, find a sub 14. So just like with the arithmetic sequences, we're going to focus on jumping. How many jumps are there to get from the 4th term to the 10th term? 6. So basically what we're saying is to get from the 4th term to the 10th term, we would multiply the 4th term by r 6 times. So to put that in notation, instead of using all those words, we would say, to get to the 10th term, we're going to start at the 4th term and jump 6 times. We're multiplying by r raised to the 6th power. So basically, when we look at this type of problem, this is going to be our first step. If we plug in what we know, given in the problem, we're going to end up with a sub 10 a sub 4 and r to the 6th. We don't know what r is yet, but now we just created an equation where it's the only unknown. And so as we solve, as we simplify, we get r to the 6th is equal to 1 over 64. And finally, r is equal to 1/2. So let's see if we can get this in order. See this? You're going to first have to come up with your very own way of using the definition of what a geometric sequence is. Then you're going to be plugging in. Then you're going to be simplifying until finally you get down to the answer. Hopefully that fit into the screen. Okay, we're not done now yet. We've got to find a sub 14. Just going to scoot this all over. And we're going to say, okay, now we know what r is. So to find a sub 14, we're going to get it, we're going to use it in a formula. And we're going to say, hey, to get to a 14 from a sub 10, we're going to do 4 jumps. And each jump, we're multiplying by r. And so here's our equation that we set up. And now we're just going to plug in what we know. We don't know a sub 14, that's our unknown, but we do know a sub 10, and we know r, and obviously 4 is 4. Which leads us to the answer of 125 over 1024. These aren't quite as intuitive as the jumping problems that we've done with the arithmetic sequences, but I think once you try a few, there's a nice flow to them. So you'll see this type in our homework during class and on our test. So the very next thing we have to talk about, because we talked about geometric sequences, is geometric sums. There are 2 types of geometric sums. There are partial sums, which we'll call finite sums, and there are infinite sums, which we'll talk about later. Finite sums are the same as taking a partial sum using sigma. And luckily, it comes with a formula. It's not an easy one to memorize, and we'll talk more in class about the need to memorize this formula, but there is a formula to find a geometric sum that's finite. And it's pretty self-explanatory. Just plug and chug. Oh, self-explanatory. The other type of sums are infinite sums, and these are a little bit more fun. Infinite sums of a geometric sequence is the same thing as saying that you have a geometric series. And to understand it, I'm going to bring back in the summation notation. It basically says that here we've got a geometric sequence, the definition of a geometric sequence, so it is a geometric sequence. And we're starting from the first term. We want to take the sum, starting with the first term, to the infinite term. That's not really a way to actually say it, but to infinity. We want to know, hey, does this geometric sequence have an infinite sum? And if so, what is it? And so that's what that's how we use summation notation to represent an infinite sum. And this, a sub 1 over 1 minus r, is the formula that we're going to use to find the infinite sum of a geometric series. That is definitely one that you want to memorize. So, if you see a problem, find the sum of the series, and you see it in summation notation, tells you a few things. First of all, we're taking an infinite sum. Second of all, it's a geometric sequence. And so we're going to use our formula. Just push it over there. A sub 1 over 1 minus r. And I'll plug in. It's my first term. That's my r. And voila, I get 10. I want you to think about that. I want you to take some time and think about it before I see you in class. We've got an infinite series, a series that goes on and on and on and on. And yet, we already know that the sum is equal to 10. Even as the series goes on as I speak. It's going on and on and on and on, and we already know that it's equal to 10. I want you to think about why that possibly might be. We're going to look at another problem where we're finding the sum of the series. So here's another problem, and once again we have a geometric sequence and we're asked to find the infinite sum. And we're going to go ahead and use the handy dandy formula a sub 1 over 1 minus r. And we plug everything in and we get -3. Okay, think about that. Just pause it for a second and think about what this means. We have a geometric series, or a geometric sequence, who is starting, the first term is 3, and the second term obviously is going to be 6, and so on and so on. But yet the sum of all of it is equal to -3. Really? Let's think about that some more. So we know that there's no way this sequence adds up, this infinite sequence adds up to -3, which asks us, which brings us to ask, when can the sum of a geometric sequence not be found? And it turns out that there are some parameters on R. The common ratio R, the absolute value of it, has to be less than 1 in order for a geometric sequence to exist, the infinite sum of a geometric sequence to exist. And so another way of saying that, because this might be confusing, and I'm not sure if you remember from Algebra 1 how we break that down to a compound inequality, but that's the same thing as saying that R has to lie between -1 and 1 in order for this infinite sum of a geometric series formula to actually give us a real, true answer. Okay, so that's it. That's the end of the lesson. It was short, sweet, to the point. So once again, your responsibility before you head to class is to watch this video, take notes, jot down any questions that you have, and be ready to come in and work on the real fun stuff, the actual problems. I look forward to seeing you in class. Thank you.